Hi everyone, today we would like to share VolcanoML, speeding up end-to-end AutoML via scalable search space decomposition. This is a quick outline about what we are going to talk about. Before walking through the details about the proposed framework, we first introduce the background and motivation. After that, we will end this talk with experiments and the conclusion. AutoML systems have been an emerging type of systems that have significantly raised the level of abstractions of building ML applications. Giving an input dataset and a user-defined utility metric, for example, validation accuracy, these systems automate the search of an end-to-end ML pipeline, including feature engineering, algorithm selection, and hyperparameter tuning. Besides, many cloud service providers, for example, Google, Microsoft, Amazon, and Oracle, all provide their services on the cloud. As machine learning has become an indispensable functionality integrated in modern data systems, an efficient and effective end-to-end AutoML component also becomes increasingly important. Through building a wide range of real-world ML applications, we realize that the default search space provided by state-of-the-art AutoML systems is often not enough in many applications. In this paper, we focus on the enrichment of the search space. However, for most of the existing systems, the enrichment of the search space often leads to a decline of performance. Taking AutoSigner as an example, we observe that, given the same time budget, the validation error rises when the number of hyperparameters goes larger. This is often caused by an inefficient search over the entire search space jointly, and we refer to this issue as the scalability bottleneck. The enrichment is only going to make the search space even larger and larger. An intuitive solution is to decompose the entire search space. It has been explored in many fields. However, without a structured high-level abstraction for search space decomposition, it's hard to scale up an end-to-end AutoML system to accommodate the search space that will only get larger in the future. To this end, we propose VolcanoML. Unlike the existing AutoML systems, VolcanoML decomposes the above search space into smaller subspaces. Further, it introduces the concept of building block and execution plan to express the different decomposition strategies. A building block can be viewed as an atomic decomposition strategy. The goal of VolcanoML is to solve the AutoML problem over the joint search space, and one building block is responsible for solving a smaller subproblem over smaller subspace. Concretely, we design three types of building blocks: joint block, conditioning block, and oscillating block. The joint block optimizes the input subspace directly using Bayesian optimization. The conditioning block further divides the input subspace into smaller ones by conditioning on one particular input variable. The alternating block partitions the input subspace into two and then optimize each one alternately. Then, we describe the execution plan in VolcanoML in detail. A VolcanoML execution plan is a tree of building blocks. The root node corresponds to be solving the problem over the entire space, which can be further decomposed into multiple building blocks if necessary. This figure presents the VolcanoML execution plan for the same search space explored by AutoSectioner, which consists of the joint search of algorithms, features, and hyperparameters. Instead of conducting the search process using a single joint block, VolcanoML first decomposes the search space via a conditioning block on algorithms. It then further decomposes each of the subspaces of feature engineering and hyperparameters tunings via an alternating block. The final subspace is optimized by a joint block. During each iteration, VolcanoML selects a leaf node and optimizes its space. In this figure, we tuned the feature engineering pipeline of algorithm 1, A1, while fixing its algorithm hyperparameters. Now, we move forward to the experiments part. As shown in Table 1, VolcanoML achieves the best average rank for both the classification and regression tasks, given the three different search spaces. This demonstrates the scalability of VolcanoML compared with the state-of-the-art AutoML systems. Figure 4 presents the results of VolcanoML compared to AutoSectioner and Teapot on the 30 classification tasks and the 20 regression tasks, respectively. The green bars indicate the relative performance gain on different tasks. Figure 5 gives the results on 4 large datasets. We observed that VolcanoML achieves very impressive results. We also compare VolcanoML with 4 commercial platforms from Google, Amazon, Microsoft, and Oracle. We observed that, given the same time budget, VolcanoML is at least comparable with, often outperforms, the considered commercial platforms. Finally, we conclude this paper with the following contributions. VolcanoML presents a scalable and extensible framework that allows users to design decomposition strategies for large AutoML search spaces in an expressive and flexible manner. Experimental evaluation demonstrates that VolcanoML can generate more efficient decomposition strategies that also lead to performance-wise better ML pipelines compared to state-of-the-art AutoML systems. Now, the VolcanoML framework has been implemented and integrated into the AutoML system malware. That's all. Thanks for your listening.